Everybody to this second of 2 webinars today that we have decided to hold to memorize or to keep the CEMCAP heritage more alive, that you get to see presentations and hear people speaking about what's been done in CEMCAP. We have 2 presentations this afternoon. It's Matteo Romano from Politecnico di Milano. First, we'll present the techno-economic analysis of calcium looping processes for low CO2 emission cement plants. Thereafter, Stefania Gardarsdottir from SINTEF will present the overall techno-economic analysis, and she will also demonstrate the spreadsheet that was developed in CEMCAP, and that's been made openly available, and she will also show you where you can find it. And after Matteo's presentation, there will be some room for a possibility to ask questions, and there will also be this possibility after Stefania's presentation. But I think we will just get started with Matteo's presentation. So please, Matteo, go ahead.
Okay, thank you. So I'm going to present the work on techno-economic analysis of calcium looping processes for low CO2 emission cement plants that involved mainly people from Politecnico di Milano, LEAP laboratory in Piacenza, and Italcementi as industrial partner. So a brief short summary of this presentation: why calcium looping cement plants, a brief discussion on the 2 possible integration options, the tail-end and integrated calcium looping configuration, key performance indicators, results and conclusions. So fundamentals on calcium looping, it's technology which is based on 2 reactors. The first one is a carbonator reactor, which is used to capture the CO2 from flue gases by means of a sorbent based on calcium oxide that reacts with the CO2, forming calcium carbonate that reacts at a relatively high temperature, around 650 degrees C. The calcium carbonate formed in the carbonator reactor is regenerated into the calciner reactor, where the reverse reaction or calcination reaction is performed. This is done by means of heat that is provided normally by Oxyfuel combustion of coal that releases CO2-rich gas ready for sequestration after some purification. The system needs a purge of a spent sorbent and makeup of fresh limestone, mainly to avoid the accumulation of ash and sulfur species that enter with the fuel inside in the calciner. The heat to be provided to the system is a relatively high amount and of high quality because it's a fuel that needs to provide heat at 900 degrees. This heat is actually then available in the carbonator, where the carbonation reaction is exothermic. So this heat must be recovered by means of a steam cycle in order to make the system efficient. Short history on the technology. It has been originally proposed by a Japanese group led by Shimizu that published in 1999 first publication on the concept on the twin fluidized bed reactor for CO2 removal. And since then, the technology has been developed for the following 10-15 years that led to the first important demonstration in the activities in power plants. So several fluidized bed pilot facilities have been built, most of them in Europe, one in the University of Stuttgart, a 200 kilowatt pilot, then 1 megawatt pilot at the Technical University of Darmstadt, and then 1.7 megawatt pilot at La Pereda power plant in Spain. And this one is a pilot plant which is connected to an existing power plant. So it's in a real industrial environment. So this was the focus initially on power plants. More recently, the interest of this technology is is in the cement industry, basically because the technology uses calcium oxide and calcium carbonate as materials that are the same materials that cement producers are used to use. So in calcium looping for cement plants, you have basically three options for the integration for their use in cement plants. The first one is actually very simple, is the use of is the integration with the power plant and the use of the calcium oxide rich spent sorbent from the power plant as feed for the cement plant, a substitute of the limestone. Actually, this option is interesting, is nice, but you need to have a relatively large power plant next to a cement plant in order to avoid difficulties in the logistics. So actually most of the work, all the work in CEMCAP project focused on the following two options. The first one is the tail end configuration, where calcium looping process is integrated as a post-combustion capture configuration in a cement kiln. And the third option is the integrated calcium looping configuration, where calcium looping is integrated in the cement plant by sharing the same Oxyfuel calciner. So this is the figure of the tail end calcium looping configuration. So basically, the carbonator is placed at the end of the production process, so it removes the CO2 from the cement plant flue gas. The integration and the retrofitting is therefore relatively easier. Limestone that is fed to the cement plant is partly calcined in the calcium looping calciner, so it is used as source of the sorbent for the carbonator. And then you have calcium oxide purged from the calcium looping process, the green arrow in the figure, that is then fed to the cement plant. The system in the tail end configuration has a high fuel consumptions, and this is due to the double calcination for the minerals you captured. So you know that in cement plant you already have calcination of calcium carbonate. You need quite a lot of fuel in the pre-calciner to release this CO2 and produce calcium oxide for clinker production. Okay, this CO2, mineral CO2, is then captured again in the carbonator, forming again calcium carbonate, which is calcined again a second time in the calciner. So basically you use 2 times the fuel to calcine twice the CO2 that originally comes from the calcium carbonate calcination. And for this reason, you have high fuel consumption on the whole. Anyway, you have high fuel consumption, but this is not waste fuel. This is not really waste heat. It is heat which is recovered in a relatively efficient steam cycle for power generation. Efficiency here will be around 35%, as we will see later on. So much higher than expected for cement producers when they consider heat recovery by organic ranking cycle, which have much lower efficiency. Here efficiency is much higher, even though not as high as in state-of-the-art large coal-fired power plants. Another note in this system, which is based on fluidized bed reactors, so the particle size is average particle size around the order of hundreds of microns. On the other hand, for clinker production, you need particle size of the order of a few tens of microns. Therefore, the calcium oxide purge from the calcium looping system here needs to be milled at low temperature before being fed to the cement plant. So, as said before, most of the research activity in CEMCAP focused on this process. There was, of course, numerical techno-economic study, which is the objective of this presentation, but of course, most of the experimental activity has been also performed focused on this concept. And this activity has been performed at CSIC in Spain and at the University of Stuttgart in Germany. So you see here 2 figures showing some experimental results. The demonstration has been performed up to TRL 6 at Stuttgart. And what had been found basically is that there were no surprises compared to what we knew from the applications in power plants. So calcium looping design parameters for cement plant applications are in good agreement with the design parameters expected for power plant operation. And you see on the bottom two publications related to the experimental activities of the two groups involved in this activity in CEMCAP. The integrated calcium looping configuration is shown in this slide, in the figure on the left. And basically, the main idea is that the carbonator is integrated into the preheater of the cement kiln, and it captures the CO2, which is originated from the rotary kiln. So the rotary kiln of gas are partly cooled in a two-stage preheater, as you see on the right-hand side on the figure, and then this gas enter in the carbonator where CO2 is captured. On the other side, on the left in red, you have the calciner that coincides with the, so the calcium looping calciner coincides with the cement kiln precalciner, which is Oxyfuel precalciner. So the calcined raw meal, which is originated in the precalciner, is split into two. One part is sent to the carbonator for CO2 capture. The other part is sent to the rotary kiln for clinker production. So the solvent here is not relatively pure calcium oxide limestone, but it is calcined raw meal, which also contains silica, alumina, iron oxide, which are normal constituents of the raw meal fed to a cement kiln. And here also we need to use small particle size, so the same particle size used for clinker production, order of tens of microns, 10, 20 microns, which means that fluidized bed here are not the best gas solid conductors, but entrained flow reactors should be used, as entrained flow reactors are already used in cement kilns, so normal precalciners are entrained flow reactors. So here there was some modeling and experimental activity performed in CEMCAP at low TRL. So one of this activity was a 1D carbonator modeling to understand what are the expected operating parameters of the carbonator to achieve target CO2 capture efficiency. So we published recently a paper which is shown below, and on the right-hand side you see a representative figure showing that with reactor lengths of around 100 to 120 meters, you can achieve a CO2 capture efficiency in the carbonator of around 80, between 70 and 90%, let's say. Also an important result of this study is that you need a relatively high solid to gas ratio inside the reactor of the order of 10 kilogram per normal cubic meter in order to achieve such high CO2 capture efficiency. And this solid to gas ratio is significantly higher than solid gas ratio experienced today in preheater and in the precalciner of conventional cement kilns. Another important issue that was revealed by experiments is that the formation of belite, so calcium silicate in the calciner, may cause the decrease of the sorbent CO2 carrying capacity, and therefore we will need controlled calcination conditions in order to avoid the loss of activity of the sorbent. As you see again on the right-hand side in the figure, the CO2 capture efficiency depends a lot on the Xmax of each curve. Xmax means the maximum conversion of a calcium oxide into calcium carbonate in the fast kinetically controlled conversion period. So low Xmax, which in this case means high loss of activity because of the light formation, may cause low CO2 capture efficiency in the carbonator. We need sufficiently high CO2 maximum conversion of the sorbent to achieve high CO2 capture efficiency. And okay, as I said before, this technology, this process has been demonstrated in the CEMCAP project at low TRL. I would say TRL of order of 3. with some experiments which are also shown in the literature below. So basically, the chemistry and the fluid dynamics of the reactors in industrially relevant condition is needed to prove the technology. And this is what will be done in the clinker project that has started about 1 year ago and aims at demonstrating this technology in a pilot plant next to an operating cement kiln. So if you're interested in this technology, follow the clinker project as well. So, as mentioned before, in all calcium looping systems, you need a heat recovery steam cycle if you want to achieve sufficiently competitive efficiency for the system, energy efficiency for the system. So, in the two processes, you end up with a steam cycle which has a different size, let's say of the order of 17 megawatt in the tail end case, where you have high fuel consumption because of the double calcination issue mentioned before. In the integrated case, you don't have any more of the double calcination issue, so the fuel consumption is lower and the electricity produced by the heat recovery steam cycle will be lower. It's around 20 megawatt electric. So for this power plant size, the steam cycle parameters will not be of the super efficient, ultra supercritical power plant, but of the subcritical power plant with an operation pressure of around 60 to 100 bar, maximum temperature of 460, 530 degrees, steam turbine efficiency 76-86%, a moderate number of feed water preheaters. So the steam cycle electric efficiency will be between 30 for the integrated case, lower power, and 36% for the higher power tail end case. So based on this, we calculated the overall heat and mass balances of the systems. Here you see the reference cement plant without capture in the first column, two tail end calcium looping cases with two different integration levels, 20% and 50%. Here, integration level indicates the percentage of calcium of calcium that enter the system through the calcium looping process. So 20% means that 20% of the calcium carbonate is fed to the calcium looping first, while 80% is fed directly to the cement kiln for clinker production. And the last column is the integrated calcium looping case. So first point is that the total fuel consumption in all of the calcium looping systems is much higher than the reference cement plant, and especially for the tail end cases because of the double calcination issues. In the integrated case, fuel consumption is much lower than in the tail end cases, but still pretty high compared to the reference cement kiln. Thanks to the power generation caused by the high fuel consumption, you can produce electricity. So you see here the net electricity consumption, which, as you see, remains close to the electricity consumption of the reference cement kiln, while it becomes negative for the tail end case with low integration level. This becomes negative means that the steam cycle produces more power than needed by the auxiliary systems. For the other cases, again, net electric consumption is similar to the reference cement plant, which means that the steam cycle is producing enough power to compensate the energy consumption of the air separation unit and for CO2 compression and purification. So then we have equivalent CO2 avoided here, which means the CO2 avoided by the whole system, also including the emissions avoided or indirect emissions from electricity production, which are here evaluated with the average EU28 energy mix. And we have also the SPECA index of around 4 for the tail end option and about 3 megajoule per kilogram of CO2 for the integrated case. Here again, also in the bottom line, publication is shown that addresses the calculation of the tail end process, while another publication is coming for on the techno-economic analysis also of the integrated calcium looping case. So for the economic analysis, what we calculated is a cost of CO2 avoided of the order of 50–55 euros per ton. This is mainly due to the capex, and this is because the technology is relatively capital intensive, because you need an air separation unit, because you need a CO2 compression unit, which are I would say larger than in the Oxyfuel plant, because here you remember we have additional fuel consumption, so you need more oxygen and you generate more CO2 than in the Oxyfuel cement kiln. And also here in the capex you also have the steam cycle that also adds some capex to the system. So in the end, yeah, this is the main result. You see that you can also have a positive balance for the electricity for the tail end cases, first two columns. The orange bar is negative, meaning that you can earn some money by selling electricity, or you reduce the cost of electricity thanks to the the price to pay for the electricity thanks to the self-production in the intermediate case. So conclusions, calcium looping process integration options. The first one is the post-combustion capture configuration, the tail end one. It has a low uncertainty in the technical feasibilities. We can say that it is ready for demonstration at a larger scale. It was mentioned this morning. It can achieve very high CO2 capture efficiency, but you need two calciners and you will have high fuel consumptions, although you can produce a quite significant amount of electricity from it. The integrated calcium looping configuration has a high CO2 capture efficiency without modification of the rotary kiln operation. You have a higher thermal efficiency and lower fuel consumption compared to the tail end option. But you have a new carbonate of design and fluid dynamic regime. So fluid dynamics, heat management, and solvent performance need validation at sufficient scale. And in the end, we obtain competitive cost of CO2 avoided compared to the other technologies, as you will see in the following presentation. So this was the last slide. I will be happy to take any questions. These are the list of the CEMCAP partners and acknowledgement to the EU.
Okay, Christine, are you there?
Yes, I'm here.
Yes,
so do we have
just a small comment? Is that Olaf Soldal? He asked a question, but I will unmute now. Olaf, maybe, so that he can ask his question. So Olaf, now you are unmuted. No, he seems that he, Christine, then you can talk.
no, I think his question was, is it possible to get a copy of the last slide? I can inform everybody that we will upload the entire webinar on the CEMCAP website.
Yeah.
So it will be available. And also the presentations from GHGT. I think the presentations will also be uploaded in PDF format, I think also.
So just to make the participants aware is that they can ask questions now by raising the hand that they have on the small dashboard just in front of their names. They can raise their hand if you have any questions. No questions?
No, I don't think there are any. I think we can move on to the other presentation then and see if there are any questions after that.
And that will be Stefania. So I am now making Stefania the presenter.
So Stefania will present the overall techno-economic study that was done, the comparative study that was done in CEMCAP.
Yes, can you guys hear me now?
Yes.
Yes.
Hello, hi. So, hi everyone, my name is Stefania and I am a researcher at Syntef Energy Research. And in this presentation, I will present the main findings from the Techno-economic comparative analysis that we carried out in CEMCAP of the 5 CO2 capture technologies that we have looked at in the project. Just a small introduction first to the project. So CEMCAP is a Horizon 2020 project. And to the right here in the figure, we can see the number of partners that have been involved, the whole consortium, which has been quite large. And the main aim of our project has been to prepare the ground for large-scale implementation of CO2 capture in the European cement industry by further developing several CO2 capture technologies for this application. And in this context, understanding costs and reducing uncertainties is a very important factor. And this has been a significant part of the work that we have performed in CEMCAP. Now, the motivation also for doing this project is the fact that emissions from the cement industry are accounting for around 7 to 9% of the global anthropogenic CO2 emissions. And of these, around 2/3 originate from the raw material itself and not from the fuels that are used in the production of cement. And this means that the use of CO2 capture, or CCS, is the only viable option for drastically reducing emissions in the cement industry as we see today. Now, the CO2 capture technologies that we have investigated within the CEMCAP project are, as listed here to the left, the Oxyfuel technology, the chilled ammonia process, membrane-assisted CO2 liquefaction, and 2 processes based on calcium looping technology. And for reference, we have included MEA-based CO2 absorption in our techno-economic assessment. Now, in the figure here to the right, you can see a rough sketch of a cement plant. And here it is indicated where or how the different CO2 capture technologies would be integrated into the cement kiln. The chilled ammonia process, or CAP, together with membrane-assisted liquefaction and the tail and calcium looping process, these are all end-of-pipe technologies and also the reference technology MEA. That means that they treat the flue gases coming right out of the stack showing here at the cement plant. The Oxyfuel and the calcium looping integrated entrained flow process are quite different in nature to the end-of-pipe technologies, and in the way that these technologies are more integrated into the core process as indicated here. And a little bit later on in the webinar, we will take a little closer look at each of these technologies and how they are integrated in the cement kiln. Now, the approach or the methodology that we have used in our analysis is described in detail in the CEMCAP framework. And this document can be found on the CEMCAP project website and also on the online repository Zenodo. And I will show you that after the presentation how to access that and see through the different reports in CEMCAP that are uploaded there. Now, the framework document includes information on, for example, the cost estimation methodology and the different assumptions that we made to carry out our analysis, but also technical assumptions and technical descriptions of both the reference cement kiln, which is shown here to the right, and this was taken as a best available technology plant, but also technical descriptions of the CO2 capture technologies. So in our techno-economic analysis, we have done process evaluations where we have put an emphasis on the energy and environmental performance of the CO2 capture technologies. And this was based on both experimental and analytical work, where we have performed, or different partners have performed process simulations for each of the capture technologies when they are applied to the reference cement plant. And the process modeling and simulations have used quite a lot of input from experimental work that has been carried out in the CEMCAP project. And then the results from these process simulations and modeling are used as a basis for our economic evaluation. We have defined several key performance indicators, and they are also described in more detail in the framework. The main ones are the specific equivalent primary energy consumption per CO2 avoided, for short SPECA. And then we have looked at the cost of clinker, which is the main product in the kiln, as you can see here to the right, and also the cost of CO2 avoided. And we have looked at the performance of the CO2 capture technologies in several different conditions or cases, and calculated our key performance indicators for these. For example, we have a base case which considers 90% CO2 capture rate from the flue gases, CO2 transport by pipeline, and steam being supplied by a natural gas boiler for those technologies that this is relevant. Then we have looked at alternative cases, for example, where we have different extent of air leakage in the cement kiln itself. We looked at optional capture rate, ship transport, steam import scenarios, and other cases. And in addition to this, we have performed a sensitivity analysis of the economic key performance indicators, primarily to various parameters and assumptions that were used in the main analysis. Now, I will focus the next several slides on highlighting results for each of the investigated CO2 capture technologies. And I'll start with the reference technology, MEA Absorption. Now, the figure here to the right shows the main features of the technology in the pink shapes and how it is integrated into the cement plant. So the flue gases from the cement kiln, which is the light blue arrow here, enters or is led through an absorber where we absorb the CO2 into a liquid solvent. And then the CO2 lean flue gases are vented out, while a highly concentrated CO2 is desorbed from the liquid solvent here in a desorber by adding heat into the solvent. And this heat is added in the form of steam. Now, the key performance indicators in the 5 different cases that we evaluated for MEA are shown in the 3 different column diagrams here at the bottom of the slide: the SPECA, the cost of clinker, and the cost of CO2 avoided. And here to the left, we have the indicators from the base case, where we calculated a SPECA of 7.1 megajoule per kilogram CO2. And we will see later on, when we look at the other technologies, that this is a quite high value compared to the others. Here we saw that the cost of clinker increased by 72% compared to the reference cement kiln without CO2 capture, and the cost of CO2 avoided was calculated to 80 euros per ton CO2. For the MEA technology, it is the cost of steam that contributes most to the cost. As you can see in the light pink here in the cost breakdown, especially in the cost of CO2 avoided. And a small part of the steam demand was covered by waste heat that was recovered at the cement kiln, but the majority has to be supplied by other means, for example, a natural gas boiler. And out of the different cases we investigated, I would just like to point out the steam import case, as it has a little bit or quite different results than the others. In this case, steam was bought from an external power plant instead of producing it from a natural gas boiler on site. And the steam was bought then at a lower cost and with lower associated CO2 emissions compared with the base case. And that resulted in a significantly lower SPECA, also a bit lower cost of clinker, and especially cost of CO2 avoided. Now, moving on to the Oxyfuel technology. In this technology, the combustion in the rotary kiln itself is performed with an oxidizer, mainly consisting of oxygen and CO2, instead of air, as is done in the reference vent kiln. And this is shown here in the process schematic to the right. Now, this combustion process produces a CO2-rich flue gas. Here, the dark line coming out from the cyclone preheater. And this allows a relatively easy purification with a CO2 purification unit to get a highly purified stream of CO2 for transport. And in this process, we need additional power for an air separation unit to provide the oxygen needed in the process, and also for the CO2 purification unit. And some of this power demand can actually be covered by recovering waste heat from the process in an organic Rankine cycle. So this generates power from the waste heat. Now, the key performance indicators in the 5 different cases that we looked at for Oxyfuel are shown here in the bottom 3 column diagrams. And here we were focusing our investigation on different extent of air leak in the core cement plant. But what we saw here, then, if we look at the numbers for the base case, that we have a SPECA of around 1.6 megajoule per kilogram CO2. Remembering what we had for the MEA case, we were around 7 there. Here, the cost of clinker is increased by 49% compared to the reference kiln, and the cost of CO2 avoided was calculated to 42 euros per ton CO2. And for this technology, the Oxyfuel technology, we did see that there was not a significant impact of air leak on the costs, at least not in the range that we investigated in CEMCAP. And we saw that both the capital costs, which are in the dark blue here, and also the operating cost, which is mainly electricity, they are quite moderate in the Oxyfuel case. Now, moving on to the chilled ammonia technology, this process operates quite similar to the MEA reference technology in a way that we have our flue gases being led through an absorber, and we absorb the CO2 in a liquid solvent, and here it is ammonia based then. And the gaseous CO2 is released or desorbed in another column here when we add heat in the form of steam to the system. Now, the key performance indicators in the 5 different cases that we evaluated here are, as before, shown in the bottom here. The SPECA, cost of clinker, and the cost of CO2 avoided. And looking at the base case numbers, we calculated SPECA to 3.8 megajoule per kilogram CO2. The cost of clinker increased by 68%, and the cost of CO2 avoided in the base case was 66 euros per ton CO2. Now, for the chilled ammonia process, we saw that there was significantly lower steam and power demand than in the reference MEA technology. And here, a part of the steam demand was also covered by waste heat from the cement kiln. And pointing out the steam import case here as well, we saw that the SPECA decreased quite a bit compared to the base case. But on the other hand, there was not as a large reduction in the cost parameters in the middle and the right bar diagrams here. And we noticed that the cost of steam does not make up for such a large portion of the total costs when compared to the MEA, for example, as the capital costs, the dark blue parts here are also quite an important factor. But still, the steam is the main energy demand of the process, and there's ongoing work for IP protection of process concepts that have been developed with improved energetic performance of the process. So that is ongoing work and future work for the chilled ammonia process. Now, moving on to the membrane-assisted CO2 liquefaction. And this technology is essentially two different technologies that are combined, so that each of them can carry out a partial separation of CO2 from the flue gases within its favorable operational regime, so to say. So the first technology, the membrane, we use a polymeric membrane for bulk separation of CO2, and that results in a CO2-rich product stream. And this stream is then sent to a CO2 liquefaction process, where the CO2 is liquefied and the more volatile impurity components are removed. And this results in a high purity CO2 product that can be led to the transport section. And this technology is an end-of-pipe retrofit technology, so there's no additional integration or feedback to the cement plant here. And we only need power as an input, so no steam is needed here. We looked at 4 different cases, and the SPECA, the cost of clinker and cost of CO2 avoided, are shown for these here in the bottom. Looking at the base case numbers here to the left, we see that the SPECA was calculated to be 3.2 megajoule per kilogram CO2. Cost of clinker increased by 92%, and the cost of CO2 avoided was calculated to 84 euros per ton CO2. And for this technology, it is mainly the electricity consumption and high capital cost. We can see that especially here in the cost of CO2 avoided, that these are the factors that contribute most heavily to the total cost. And I think maybe pointing out one of the cases, the low air leak in the mill case, for example. Here we can see that the process performance, both technical and economic, was seen to benefit from a lower air leak in the cement plant, and this results in a higher CO2 content in the flue gas coming into the membrane and into the process as a whole. But also in general, we also saw that the membrane performance is critical, and that it strongly affects the electricity demand of the process. And also the membrane has a significant capital cost. So that is quite an important or integral part of the whole thing. Lastly, I should mention that this technology has a relatively low maturity, and there are relatively large uncertainties and added contingencies in the capital costs. So with further development of the technology, we at least would be able to reduce these uncertainties even more, and perhaps see an improvement in the capital costs. Moving on to the calcium looping technology, as my colleague Matteo described before, this technology is based on a reversible carbonation reaction. So it means that the formation of calcium carbonate from calcium oxide and CO2 is used to separate CO2 from the flue gases. And the process is carried out in 2 interconnected reactors, as we can see here in pink in the process figure, the carbonator and the calciner. And in the tail end configuration, we have the flue gases directly being led into the carbonator, where they react with a calcium oxide-based sorbent, and then form the calcium carbonate, which is transferred to the next reactor, the calciner. And there we heat up the material and reverse the reaction. And by doing so, regenerate the sorbent that is sent then again to the partly to the other reactor. And we also produce a CO2-rich product stream that can be sent for further purification and then to transport. A part of the calcium oxide from this system is purged and sent to the cement kiln, as we can see here in the darker blue arrow leading back to the raw mill. And the integration level, or let's say the fraction of the calcium oxide purge from the calcium looping system with respect to the total amount of material sent to the cement kiln, that is quite an important factor for this process. And Different cases with different integration level were investigated here. Now, the calcium looping process requires limestone and coal to operate, but it also needs oxygen in the process, as we have oxyfuel-based combustion in the calciner. And let's see, the power is also, so there's power requirement in the ASU, the air separation unit, the core calcium looping process itself, and for the CO2 purification unit. But then again, we have a considerable amount of power being generated in a steam cycle, which recovers heat from the system. Now, the key performance indicators in the 3 different cases that we investigated here are shown in the 3 diagrams in the bottom. And looking at the base case numbers here to the left, the SPECA was calculated to be 4.1 megajoule per kilogram CO2. The cost of clinker was seen to increase by 66% compared to the reference cement kiln without CO2 capture, and the cost of CO2 avoided was calculated to 52 euros per ton CO2. Here, the consumption of coal is a significant factor with respect to SPECA and also to the respect of cost of clinker and cost of CO2 avoided. Also, the generation of electricity in the waste recovery steam cycle is very important, since there is quite a large amount of power that can be produced, and this depends a bit on the integration level, but it can actually result in the plant being a net exporter of electricity, such as was seen in the case of the 20% integration level. Now on to the last capture technology. The integrated entrained flow calcium looping technology is a version of the calcium looping technology where the CO2 capture calciner, which is shown here in pink, is combined with a calciner in the cement kiln itself. So it's therefore an integrated part of the whole cement plant. And as a result, the carbonation and calcination must take place in entrained flow reactors. And as for the tail end configuration, we need additional fuel for operation of the calciner, which is indicated here. And oxygen is required and supplied from an air separation unit, which needs power to operate. We also need power in the CO2 purification unit and some little power in the core calcium looping process itself. But again, as for the tail end configuration, we produce quite a lot of power in the steam cycle here that utilizes the waste heat from the process. And here we looked at 2 cases, the base case and ship transport. And looking at the base case numbers, we get SPECA of 3.2. The cost of clinker was increased by 73%, and the cost of CO2 avoided was calculated to 59 euros per ton CO2. So for this configuration of the calcium looping technology, coal consumption is also an important factor, but it's not to the same extent as for the tail end configuration we saw before. But on the other hand, there's also less heat recovery and less power generation in the steam cycle. For this technology, the capital costs are contributing quite significantly to the total costs of both clinker and CO2 avoided. I think it's easier to see it here to the right on the CO2 avoided cost. And we see that the variable costs are quite smaller. So similarly to the membrane-assisted liquefaction technology, this process has relatively low maturity, and thus there are significant uncertainties and added contingencies in the capital cost included here. To summarize the main results from our assessment, the cost of CO2 avoided for all the technologies in the base case is shown in this figure, and broken down into the different bits that make up the total cost. And we saw that the cost of CO2 avoided lies between 42 euros per ton CO2, which was for the Oxyfuel process. And that is approximately half the cost that we got from the reference technology MEA. And then up to 84 euros per ton CO2, which is in the membrane-assisted liquefaction process, and that is on the same level as the reference technology. So what we can kind of clearly see from this picture is that comparing our technologies, that different factors affect the technologies to a different extent. So, for example, in the case of MEA and chilled ammonia, steam is a significant factor, although for the chilled ammonia process, the cost of steam and the associated emissions from steam supply are significantly lower due to the lower heat requirement of the chilled ammonia process. But on the other hand, the capital costs, the dark blue area here, is larger for the chilled ammonia. For Oxyfuel, electricity consumption, which is primarily for the air separation unit and the CO2 purification unit, those are responsible for almost all the variable operating costs, and the rest is the capital cost and some fixed operating costs as well. So electricity and the capital costs are also the biggest factor for the membrane-assisted liquefaction technology, as you can see here. And here the capital costs and actually consequently the fixed operating costs are contributing to an even larger extent than compared with the Oxyfuel case. And finally, for the two calcium looping technologies, coal consumption contributes quite a lot to the cost of CO2 avoided, together with the capital costs. In both of these technologies, we generate quite an amount of electric power, and the generation in tail end case actually covers both the demand for the capture process itself and a part of the cement plant's demand. And as a result of that, we can see negative CO2 avoidance cost associated with the electricity consumption in the tail end process. Now, for the electricity intensive technologies such as Oxyfuel and membrane-assisted liquefaction, the characteristics of the electricity system and its average CO2 emission intensity is important and influences the CO2 avoided cost. This effect and impact of other parameter variations were also investigated in a sensitivity analysis. And I just wanted to very briefly give some examples from this sensitivity analysis that we performed. So looking at, for example, the picture here on the left top of the slide, we see the sensitivity of the SPECA to different types of electricity systems or electricity system characteristics. That's basically meaning the average efficiency and CO2 emission intensity in each of these electricity generation systems. So in the base case, we have used the reference value for the 2014 EU power system, and that is shown in the green bars in the middle here. And then we have included in this figure two other alternative systems. One is based on subcritical coal, shown in the dark blue bar, and that one has poorer efficiency and higher CO2 emission intensity, while the yellow bar represents electricity generation from renewables. And overall, just wanted to point out that we could see, for example, for Oxyfuel and membrane-assisted liquefaction, that these technologies are really strongly influenced by the power system and the power system characteristics. Other parameters that we analyzed were, for example, this cost of steam, shown here to the left bottom, and this one only affected MEA and this chilled ammonia technologies. We also looked at electricity prices, and this affects all the technologies, but to a different extent. And then, for example, we looked at the implementation of a carbon tax, showed here to the top right. And here, naturally, the cost of clinker in the reference cement kiln, which is the dark line here, is much more sensitive to a carbon tax than the cement kiln with any of the CO2 capture technologies. And at a tax level of roughly 40 euros per ton CO2, the cost of clinker in the reference cement kiln starts to exceed the clinker cost with Oxyfuel. And at around 75 euros per ton CO2, the cost of clinker in our reference cement kiln has exceeded the clinker cost for all the CO2 capture technologies. Now, to briefly summarize the whole work that we have performed here, what we have done, we have developed a consistent and transparent methodology for cost evaluation, and this methodology is summarized quite well in our framework document, but also in this report that we will put out in a couple of weeks or so, or in a few short time. And this methodology can be used in future projects and in in-house evaluations of CO2 capture in the cement industry, and we would be happy to see people use it. Furthermore, we have seen that our techno-economic results are sensitive to various assumptions, and the more integrated technologies appear to be more promising from a cost perspective. However, as was discussed in our webinar on the retrofitability this morning of the CO2 capture technologies, we know that there are other important aspects in addition to costs that have to be considered when we do a final plant-specific evaluation, which must always be taken. And I think with this, I would like to conclude this part of the webinar and just again point out to the final report that will be available quite soon. And we will share it on the CEMCAP homepage and also on the Zenodo platform. And finally, just to thank all the CEMCAP partners for a nice collaboration and acknowledge the funding bodies of the European Union Horizon 2020 program and the Swiss State Secretariat. So thank you for listening. And maybe before we take any questions, I should show the Excel spreadsheet or the economic model that we have used. Anne or Christine, does that sound
please.
like
I think you should do that first.
Yeah.
Yeah.
Then I will do that. Let's see if I can do like this. So just first to show you the Zenodo platform, which is simply found on zenodo.org. I think the easiest way is just to simply type CEMCAP in the search file here. And then you should get all the different reports and documents that we have published from CEMCAP. And just if we scroll down a little bit, we can see the CEMCAP economic model spreadsheet. And from here, it's just quite easy to download, and then you can use the document or the model yourself. Now, the model looks something like this. There are several tabs here that we can see. The first one is just some version information and about the people who have been working on this. But the second tab is the instructions, and here are quite nice step-by-step instructions for the whole spreadsheet. But we can just go through these kind of quickly. So there are green cells in the other tabs that we will look through, and those indicate where one should enter the input data to the calculations. There are firstly light green cells, and those contain CEMCAP reference values. So if you want to use the CEMCAP framework and the values that we have used in our analysis, these light green cells should not be changed. But if you do change something and then you would like to calculate again with the CEMCAP value, then it's just to click this button here, Restore CEMCAP Default Values, and those will be restored. The dark green cells show the main input cells where the user should put in information. And here you can basically see the step-by-step instructions here, but let's just move to the first input tab, the utilities and consumables. So here, I hope everyone can see it maybe a little bit smaller. Let's make it a little bit bigger. Here the user can add different items that are associated with the capture plant. So the light green cells here are what the reference cement kiln is using of different utilities and materials. But then the dark green cells is what we would like as a user to add. So for example, we have maybe a process that uses a little bit more fuel and maybe uses a little bit more electricity, maybe some steam, maybe some cooling water and different things. And then if you have other things, you can add them to the lines here below the yellow line. So then you would need to add the cost per unit and the amount, the unit amount per ton clinker. And if you would like to add something else, for example, climate impact, you can do that here. To the right in this tab, we have some different power generation systems that you can choose between. This is basically what I showed in the sensitivity analysis slide before. So here in the base case, we used the EU 28 in 2014. And then you have the associated efficiency and the associated specific emissions. And here below, we have what kind of reference steam generation costs and emissions we have. Now, in the next tab, you will be able to enter the carbon tax, if you like. And as you can see here, a price of steam with carbon tax is calculated automatically here. But in the next tab, we will introduce the carbon tax. So let me just make this a little bit bigger again so we can see. So here we have a whole lot of parameters, but there is not necessarily that much that one would like to change. Perhaps a capacity factor or a tax rate or some of those different financial data could be of interest. But if you're doing a quick evaluation with the CEMCAP framework, then you only need to look at the dark green squares. And these are, for example, how much clinker is produced in your plant. And if you have an end-of-pipe technology, this would probably not change. But if you have a more integrated technology, this might be influenced. This is important, the emissions, direct emissions at the stack. And then we have here on the right side in this column different things regarding the capital costs that we would like to add. Here it is mainly the total direct cost of the CO2 capture plant. And you might want to change factors for indirect cost, owner cost, and project contingencies. These are added cost factors that together will make up the total planned cost in the end that is calculated. So maybe our process costs 150 million euros, for example, and we might want to have a carbon tax, maybe 20 euros. Let's just make an example. And then lastly, the number of persons working in your cement plant when you have added the CO2 capture process. So in the reference case, we have 100 people, but then you might want to add some more workers. And to calculate the cost of clinker and cement, which is shown here to the right, and also the cost of CO2 avoided, you just simply click the dark blue button here at the top of the page. And in a matter of seconds, you will have a new calculation. And there you can see a rough breakdown of the different cost factors that make up the total cost of clinker, cement, and CO2 avoided. Just lastly, I would like to show quickly the sensitivity tab. And I will also make this a little bit bigger. So here you can quickly make a sensitivity analysis of several of the important cost parameters: the fuel cost, electricity price, carbon tax, and variations in the capital cost. And then you can add yourself what you want to have as the range of each of these variables, and just simply to click the button and it will calculate the sensitivity. And so the pictures here to the right show the cost of cement in the reference cement kiln without CO2 capture and the cement kiln with the CO2 capture system. But the table here to the left also shows the cost of CO2 avoided in the different cases. So I think that is it for this demonstration. And maybe if there are any questions on this or on the presentation that I had before, I think we can just go ahead.
Thank you very much, Stefania. Are there any questions to this very interesting presentation?
Johannes has a question, so we'll unmute him now. Johannes, there you go.
Yeah, hello. First, I have a very brief remark to the very first slide where it said 7 to 9% of CO2 emissions attributed to the cement industry, and this number should be corrected to 6 to 7%.
All right.
And the number of 6 to 7%, which is a correct one, this is excluding recarbonation of concrete, which might, if you account for that, even lower this number by 10 to 20%. But this is the correct range here. Yeah. And then I have a second question, which is on the Excel sheet, actually.
Yes.
And the value that was entered for the cost of CO2 had the unit of kilograms, which I think the number that was there should perhaps refer to tons.
Yeah. That is true, and I think this is per ton, I am pretty sure, but we should...
the unit should be...
Absolutely, we should update the sheet. Absolutely, yeah. We will make a new version. Thanks for the comment, Johannes.
Thank you,
okay.
Johannes.
Any other questions?
There are no hands raised, Christine, so...
Yes. Does everybody know how to ask the question? There's a button on the panel with a little hand. If you click on it, you can ask a question.
No.
No.
No question.
No questions. I can just to add, because Stefania mentioned and was mentioned earlier today also that we'll put deliverables in this Zenodo platform. That we do when deliverables are approved by the European Commission, but we put deliverables on the CEMCAP website immediately after we have submitted them to the EU. Then we have to wait for a while for approval. But once they are in Zenodo, you know that these are really the final deliverables, final versions, and final outcome of the CEMCAP project.
I see that Johannes has one more question, so I'm unmuting him. Johannes?
Yeah. One more question to the procedure for steam import, which was relevant for several of the technologies and the specker identified for them. I guess that when the steam import is done, that still the megajoules for the fuel that is used in the power plant providing the steam is accounted in these numbers. And then based on that, I'm really surprised about the big difference that is here visible now for the MEA technology, that actually the specker is more or less halved when the steam is imported from the power plant, which would mean that the power plant is double as efficient as if the steam is produced on site at the cement plant. Is that the right conclusion that I take from this figure?
That's a good question. I think I might almost want to give the question to Mari, my colleague sitting next to me here.
I will unmute. Mari, I unmuted you.
Yeah, so yes, the fuel is accounted for, but when you use the fuel in the power plant, you generate steam at a high pressure. And then first you generate some power, and then when you take intermediate pressure steam and use it in the capture technology. So this means that that for the fuel that you use, you get some power that you can sell and some steam for the capture technology. So that's why you have such a good performance in this case.
Yeah, so it's the dual product of the power plant, which is making the steam export from the power plant so beneficiary here.
Mm.
Okay.
Any other questions from the audience?
No questions, Kristin?
No, in that case, I think we will end the webinar here. You can always contact us at SINTEF if you have any other questions about CEMCAP. You'll find our contact details on the website. And that's it for today. Thank you for all your interest. You will be notified when the webinar recording is available also. And we will also upload these two webinars and also other recordings that we made without audience of other presentations in CEMCAP. We will upload these to the CEMCAP website quite soon. Okay. Thank you very much for your attendance. Bye, everybody.
Goodbye.